So on Wednesday, we were not able to cover this little section on Newton's method, so I'll do this now. Write out these examples, upload, link to this video, all of that. And then we can finally say that we are done with applications of differentiation. So today we're going to be looking at Newton's method. So this is a way that we can find approximate solutions to the equation f of x is equal to 0 for a differentiable function f, so finding roots of that equation, by using tangent lines to the function close to the x-axis. So the way that we do this is that we make an initial guess at a root. So in this example here, if this is our function f, our root that we actually want to find is here, this x-intercept, and our first guess is going to be x1. Then we can calculate what the linearization of our function at x1 is, so this tangent line. And then what we'll do is we'll find what the x-intercept of that tangent line is. We can see that this x2, so this root of the tangent line, is closer now to the actual root that we want than the initial guess. Then what we can do is we can repeat this procedure. So now that we have the second guess that we got by using the tangent line, and the calculations to do so are here, but we'll see that there's a nice formula that we can just kind of use in general. So now that we have the second guess, we can repeat the procedure. So what we'll do is we'll look now at the tangent line to the function at that x value, and then look at the x-intercept of that tangent line. So here we're calling that x3. And so that's essentially our third guess of the root. And these guesses are getting us closer and closer to the actual one. And we can just repeat this process, finding an x4, x5, x6, until we get something that's close enough. And the way that we'll do that usually is we'll compare the decimal places of our guesses. And if we start to see that they get to be pretty similar, or it's like we get the same first 4 decimal places, then it's like, okay, we're probably close enough, we can stop now. Now, solving for the roots of this tangent line, you can see that, for this example, we start off with the equation of the tangent line at x2, and then we rearrange it, after setting it equal to 0, and we solve for x3. But this just says x2 minus f of x2 over f prime of x2. And that looks a lot like the formula that we had for x2 to begin with. It's x1 minus f of x1 over f prime of x1. And so it turns out we don't actually have to keep solving these equations and manipulating and all of that from scratch. We can just say that the terms of this sequence of guesses, so the guess xn is based on the one before it, as the guess before it, xn minus 1, minus f at that guess over f prime at that guess. So then all we really need to do is choose an initial guess, calculate the derivative of the function, and then just keep plugging things into this nice formula. Now, depending on how we've chosen our initial guess, we might actually get something that's way off, where our tangent lines are actually pulling us further away from the root. The pre-class notes have a cool way that we can see this kind of condition on convergence. But we will not go over that now. We'll just dive into some examples. Now, the way that we will say that we have reached whatever level of accuracy that we want. So let's say we say that we want our guess to be accurate to 7 decimal places. Then what we do is we stop this procedure when successive approximations xn minus 1 and xn agree to 7 decimal places. So we're going to do that now for number 1 here. We want to find an approximation for pi to 5 decimal places by solving this equation using Newton's method. So let's do this. What I'll do is, just to kind of keep it top of mind, I'm going to rewrite this formula for each guess. So we say that xn is equal to xn minus 1 minus the ratio between f of xn minus 1 over f prime at xn minus 1. All right, so here our f of x then, because this is the equation we're trying to solve, f of x is equal to 0. We can see that f of x is equal to sine x, and so that means that our f prime of x is equal to cos of x. I guess what's interesting here then is that when we get this part of the formula that's f over f prime, we can see that f of xn minus 1 over f prime of xn minus 1, that's going to be equal to sine of xn minus 1 over cos of xn minus 1. Sine over cos, we already just know as tan. And so we can already simplify this Newton's method formula for each iteration by saying that the next guess is just the one before it minus tan evaluated at that value. Okay, so we can now, I guess, pick a first guess. Maybe we can start with 3. 3 is a number that we'll know is pretty close to pi. Now, if we're trying to think of like the context in which we're doing this, I guess, let's say, I don't know if you did this in like elementary or junior high, but you tried to find an approximation for pi by finding real life circles in the world and being like, okay, I'm going to measure their circumference of the circle and its diameter and compare the ratio, because we know that circumference is equal to 2 pi times the radius. So I guess just pi times the diameter. I'll write it like that. And so if you're trying to do that with real objects and you're then seeing that pi is equal to circumference over the diameter, then if you do that and measure real life objects, you'll be like, okay, it's got to be 3 point something, you know? But depending on how accurately you're measuring, you might be a little off in terms of pi exactly. So if we're doing that, I don't know. This isn't necessary. This is just kind of trying to provide some context for how we might be trying to guess what pi is. So we'll guess that pi is equal to 3. So what we can say then is that our x1 is equal to 3. And now we can just apply our formula here. So x2, by definition then, is the guess before it minus tan at that guess before it. So that means here we'll have 3 minus tan of 3. And so if we actually see what that is as a decimal, it gives us 3 point, and I've already calculated these, 3.142546543, and it continues. Okay, so that's our first guess. This does not agree with 3 for any decimal places, so, you know, we have to keep going. And let's do x3. So x3 will just be x2 minus tan of x2. So, okay, maybe, forgive me, I'm going to copy and paste some numbers here, but I guess because we're doing this as a video and not in class, it should be okay. So our x3 is equal to that minus tan of x2. So let's duplicate this again. And if we actually see what that number is, that should give us 3.14159. Oh, this is looking kind of familiar to what pi actually is, right? And if we look at the first, it was 5 decimal places. Let's see what we have. Okay, so these agree to the first 2 decimal places. So that's not good enough. So now we'll have to do x4. And again, just use this formula. So we have x3 minus tan at x3. So that's our 3.141592653 minus tan of the same. That's just the previous guess. And then if we do plug that into a calculator, what we get is 3.141592654. And so because these first 5 digits agree, then that means that we are going to use that as our, or we have a good enough approximation. We don't have to round up or anything because we have 2 there. So we can now say pi is approximately 3.14159. And we got that using Newton's method. Cool. So that's our first example. Let's pull up our second. Now for this one, we're trying to approximate the 5th root of 10. Now, if we were trying to do this, or I don't know, if we were trying to find what this number is, we know that this is some value x. And now we want a equation that it satisfies. Now we don't want to just say like f of x is equal to x minus the 5th root of 10, because we'll still need to use some kind of numbers. Like it's just not going to make any sense because we don't have any idea of what this number actually is. So instead what we'll do is we're going to take each side to the power of 5. So we know that x to the 5 is equal to 10. And so we've got x to the 5 minus 10 is equal to 0. And that's going to be our f of x. I guess for kind of more context for why we don't use f of x is equal to x minus 5th root of 10, because, I don't know, if you wanted to evaluate like f of 1 is equal to 1 minus this, you know, if the whole point is that we're trying to approximate that, why are we using it in the equation? If that makes sense. Like, the whole point of approximating it is that we don't know what it is, so it doesn't make sense to use it this way. Okay, so instead we will use this choice as f of x. Okay, so like we saw before, what we'll also need is the derivative. So if f of x is equal to x to the 5 minus 10, f prime of x is equal to 5 times x to the 4. Okay. Okay, so now what we can do is, I guess, just decide on what our first guess is and start using our formula. So one thing we can do is we can see, let's see, so a reasonable first guess, we want to have something that's not going to be too far off, right? So 1 to the 5 is, of course, 1. 2 to the 5, if you want to multiply that out, is 32. So first guess, then, we want to choose something between 1 and 2, because we want it to have, when you take the fifth power, to actually get 10. You could try 1.5, but I think just to save some time, we're going to use the fact that 1.6 to the power of 5 is equal to 10.48576. So this is pretty close to what we want, right? We know that we want some number where you take it to the fifth power, you get 10. This is pretty close to 10. So I think this is a nice first guess. Okay, so that means we've said that x1 is equal to 1.6. So x2 is 1.6 minus f of 1.6 over f prime of 1.6. So that's 1.6 minus 1.6 to the 5 minus 10 over 5 times 1.6 to the 4. And putting this into a calculator, we get 1.58517578125. Okay, I'm thinking about it. I guess one way that we can, like, think about these problems is, let's pretend we have, like, a really dumb calculator where it can't do that much. So let's say we have a calculator that can do exponents, but it can't do roots. Or even, no, I guess we don't even need exponents, right? It's just like you're multiplying something by itself 5 times. You know, we can do simple exponents, but we can't do fractional exponents or roots. So it's like we're trying to find a way that we can estimate it using that, like, technological imposition. Yeah. Okay, so that's our x2. Now, because we were trying to approximate to 6 decimal places, here we don't match any decimal places compared to x1. So let's get another guess going. x3 will be, okay, I'm not going to write out that whole decimal again. It's just going to be x2 minus, well, I guess f of x2. So x2 to the 5 minus 10 over 5x2 to the 4. Putting in that x2 that we just found, that long decimal, what we get is 1.584893291. Okay. So here we see that we are agreeing to, so we wanted 6. I'll just underline the first 6 so we can compare. Oh, maybe you can highlight for this one. So here we see that we match the first 2. So that's okay. That's not too bad. But we want a little bit more accuracy. So let's go again. Find our x4. So we'll use the same formula. It's just the previous guess minus f at the previous guess over 5 or over f prime at the previous guess, which in this case is 5x3 to the 4. Putting that in a calculator, what we get is 1.584893194. And so if we look again at these first 6 decimal places, we see that we now totally match. And that means that we've finished finding our approximation. We can say then that the fifth root of 10 is approximately 1.584893. Cool. I did check what the real answer is. So the actual fifth root of 10, turns out that's equal to 1.584893, as we thought. And then it goes 1, 9, 2, 4, 6, 1, 1, 1, 3, 6, so on. So, you know, we're close enough. That's fine. Awesome. So those are our two real, like, Newton's method examples. I think you'll have some E-class online questions, and I'm trying to remember if it's on the written homework. It might be. But main thing you need to know is this formula. Because, of course, I'm recording this and we're not in class, we will have time to do the if time permits problem. So let's take a look at that. Okay, so example number 3 here, we're given this function f of x. It's equal to root of x for x greater than or equal to 0, but it's negative root negative x for x less than 0. If you wanted to sketch out what this looks like, so you can see that for positive x, it just looks like the normal root function. But then for negative x, we get the same graph that we would if we reflected it about both axes. If you use your like high school kind of transformations knowledge. I'll draw that a bit nicer. There, so that's our graph for f of x. We're asked to apply Newton's method to the equation f of x is equal to 0. What do you observe? Now, just looking at this equation, we know that the root to this equation is 0. We can put 0 into this function, it's 0. So, but let's see what would happen if we tried to use Newton's method to it. Well, we can start off by calculating what our derivative is. Maybe not real, maybe I'll use actual, because real has a meaning. Well, we're going to just use Newton's method for fun, see what happens. Okay, so for positive values of x, we get 1 over 2 root x as our derivative. And then for negative values of x, or I guess I'll write if again. Okay, and then for negative values of x, what we get is negative 1 over 2 root negative x times negative 1. And so we can just simplify that. And we see that we have 1 over 2 root x if x is positive. And then we have 1 over 2 root negative x if x is negative. Now, what we can do is let's actually see what our xn formula looks like. So we know that's xn minus 1 minus xn minus 1 over f prime at xn minus 1. Let's break up into two cases. So we know that's just going to be xn minus 1 minus root xn minus 1 over 1 over 2 root xn minus 1 if x is positive based on this, and then it's xn minus 1 minus root of negative root of negative xn minus 1. Oh, sorry, I wrote x positive, I mean xn minus 1. If you want, you could just do this by breaking it up into two cases, but I'm kind of just handling both at the same time. And I'll show you what we end up getting. Okay, well, if we simplify both of those fractions, what we end up with is xn minus 1. I guess we can simplify kind of to the side. Here we get root of xn minus 1, then times 2 times root xn minus 1. So that's 2 absolute value of xn minus 1, but because xn minus 1 is positive, that's just 2 xn minus 1. So that's nice. Let's see what we get for this one. Well, you would have negative, I'll give myself some more space, negative root negative xn minus 1 times 2 times root negative xn minus 1. And so then that would just give us, if we combine things, negative 2, then I'll go really carefully here. So we have the root of negative xn minus 1 squared. And as we've seen, that's the same thing as absolute value of negative root n minus 1. I guess this negative, we kind of get rid of with the square, so we could get rid of that. But the point is, because xn minus 1 is negative, we need to have a negative here so that this is positive. So this becomes, we get those two negatives, so this is also just 2 times xn minus 1. And so because we get the same thing for both cases, that means that we have xn minus 2, it's xn minus 1. Xn minus 1 minus 2 xn minus 1. And we're getting this just assuming that our guess isn't 0, but I mean, that makes sense because we don't want to guess 0. So it's negative xn minus 1. So this just tells us that the next guess is just the negative of the one before it. Well, that's weird, isn't it? So let's see what this would mean. So if we had some guess x1, x2 would be negative x1, x3 would be negative x2, but that would mean it's negative x1, so it's just the same as x1. We're just back to our first guess. And we'll never make any progress. We'll never actually converge to the real root, which we know was 0. So here, like, for instance, if we said, okay, let's start off with 1/2. Then x2 would be negative 1/2. x3 would be positive 1/2. x4 would be negative 1/2. We never converge to actual root, which we know is actually 0. Like, this function goes through 0 at 0. So we get that kind of weird behavior. Yeah, see if you can think about why that is. There is a way that you can see why this ends up happening. Think about what the slope of these tangent lines is, maybe. I don't know. If you end up thinking about that and come up with something, let me know. But I guess that's it then. This is it for our whole chapter 4. And now we can just only think about integrals for a little bit. Great, thanks for watching.